number 1, the clock will be low, and so the PMOS will be on, and it's going to pre-charge the output, so the output will be high. Then in the second half cycle of the clock, if the input happens to be 1, it can discharge the output, okay, and perform the regular logic function, which may or may not discharge the output. So this is the basics of the dynamic logic. Now the trick here is that in the next half cycle, the P is going to turn on again. Hopefully the input does not create any contention, and therefore the output will be charged. Yani the clock will be 0. The input is also 0, and so the output will be charged back, awaiting to see what is the value of A, يا 0, either 0 or 1 or 0, pardon me, and therefore either discharging the output when the clock turns on and or keeping it the same. Okay, so therefore clock low, PMOS is on, clock high, PMOS is off. Okay, now what's happening here is that if we are evaluating, then at every clock cycle we are really charging the output node or charging the capacitor. Okay, so the weaknesses or disadvantages of the domino dynamic logic is that it incurs dynamic operation or dynamic power. However, the advantages, in addition to those of the ratio logic, where I have only an NMOS logic block, I do not have any static power consumption, and also I don't have excess number of transistors, as was the case in the differential amplifier. So this allows me to have faster operation because I'm not loading my signals. Okay, and these circuits are typically preferred in critical path. If I have a critical path where I want to enhance the delay, I apply such circuits. هلا, two things. How do I guarantee that the input is not always high? And what if it were a primary input which was always high? So we know clearly that when the clock is low, the PMOS will be on, and so it's charging the output. Now if the input is also 1, it's going to try to pull it down, so there will be a contention. So this is typically resolved by adding a footer transistor to the NMOS block, which is also connected to clock. Okay, so what happens is that during this time here, the P will be on, but the N will be off. So the clock N will be off, which is this N1, okay? And so the P will be on and the N will be off. Since the N will be off, there is no path to ground, and therefore even if this primary input is equal to 1, really the output node does not have a path to ground. Okay, so under this scenario here, the output will be pulled up by the PMOS. Okay, and then when the input, when the clock becomes 1, then N1 will be on. Okay, and the PMOS will be off, and therefore what is going to happen is that this will connect my output. This will connect my this will connect my output to ground. Okay, therefore let me repeat it here. So the idea is that when the clock is low initially, the PMOS is on, the NMOS is off, and therefore I don't have path between out and ground, I only have path between out and VDD. Whereas when the clock is high, then this will be on, and so I will connect it to VDD and this will turn off. And of course I will connect to VDD depending on what my input is. And if this is connected and the clock is high, okay, then the two NMOSes will be connected. So this is N2, N2 will be on. Okay, فإذا by putting this footer clock, I protect my circuit against cases where the input might be on when the clock is low. So this way I isolate the output from ground through this clocked transistor, footer transistor, which is clocked. Okay, so this is one thing. Now a better or improved form is known as the domino logic. It is known as the domino logic, and by domino it is we mean that there is an effect that moves across the stages, and we do this by introducing an inverter at the output of every stage. So this is a clock, this is in, and this is VO1, and this is node Y. And then if I want to interface this with another domino logic gate, this will be clocked. Okay, and this will be, there will be an inverter at the output Y2, and this is VO2. And now let us assume that we are building some function that is just basic inversion, and this is VO1 is connected as the input to the second stage. No. What we notice in here is that when the clock is low, all the outputs, all the nodes Y, for example, node Y, is going to be charged up via the clock, so it's going to be high. Okay, and accordingly, node VO1 is going to start as low, and it is the inverse of Y. Okay, so now what we notice, since if this is a 1, this is a 0, this means that it will not turn on the NMOS when the clock is low. Okay, and therefore the clock for the second PMOS transistor can pull up, okay, the output Y2, and as such Y2 will be also charged high, okay, and VO2 will be automatically low during this stage. So what we notice here is that the presence, okay, so what we notice here is that due to the inverter, okay, the output of the domino gate is low, and hence the inputs to later stages will be 0 during the pre-charge, يعني لما the clock is equal to 0. So when the clock is equal to 0, what is happening is that it's pulling up the intermediate node, the inverter is setting the output to 0, and this inverted Y is being sent to other pull-down stages, which will not be activated when the clock is trying to pull up all the domino outputs or all the domino internal nodes to high, and therefore maintain the outputs during the pre-charge phase as low. So this is one property of the domino logic, and it guarantees that we turn off these and most devices. Another property is that this now prevents any contention, and also what happens when the devices turn if during evaluate phase. Let's see. Okay, so now let us assume that my input satisfies that it is low during the low clock and it only possibly rises during the high clock. So A and B will be high so initially this will be 1, okay, Y will be 1 when the clock is low. So initially when the clock is low, this will be 1, and the inputs are 0, 0, so there is no contention, so this will be pulled up to 1, this will be 0. And now then what happens is that the clock turns on, and so the PMOS path turns off. Now if A comes out to be 1 and B comes out to be 1, then it is going to pull down the output. It pulls down the output, the 1 becomes a 0, okay, and then the 0 becomes a 1, okay, and if I happen to have also C to be 1 during the high clock, if this is also a 1, then 1 and 1 will pull down this output. Okay, so this is how the chain effect, how the domino effect happens. يعني the evaluation of one stage that due to A and B is going to result in an output that will be 1, which will also result in the pull down of another intermediate node, and therefore the rise of the output of the second stage. فإذا when one stage evaluates, triggering the output to rise, and the second stage, and this effect will propagate to the second stage, okay, and this effect will propagate to the second stage, hence what we call the domino effect. Okay, so one stage will evaluate, triggering the other to evaluate as well. Now, let us take another example here where let us assume that B is 0 all the time. Okay, so what happens when the clock is low? These nodes will be pulled up. The PMOSs will be on. And then when the clock turns off, the PMOS turns high, the PMOS will be off. And so this path will be disconnected. Now we have A is 1, B, so this was initially 1. Initially this was 1. This was pre-charged high. And now what we have here now, A is 1 and B is 0. So there is no path here, and therefore this node will remain 1. So what will happen is that node Y, which was pre-charged when the clock was low, will remain 1. Okay, and node out will remain 0, and therefore this device will not turn on, and this node will remain 1, and this node will remain 0. And so the domino effect will stop. So basically, depending on the value of the inputs, they may or may not discharge the node, and therefore the output may or may not propagate to the next stage. Okay, as in here we saw an example where A and B were 1, and this led to discharging this node, raising this, which also this in this case is pulled down this node and the output rose, whereas when B is 0, it prevented the discharge of this node, the out remained 0, and therefore this lock did not evaluate. Okay, so this is why we call it domino logic. It helps things propagate through the stages. It prepares the output. The final output of every stage of the domino logic is either 0 or 1 during the evaluate. So let us now recap or summarize the findings. Then we will add an inverter. We will add an inverter in addition to the clock. And the clock can go to the PMOS, and it can also go to a footer device. This is typically done for primary input type gates, where my input is coming from anywhere, so the clock will be maybe like this, and the input can be still high, and I will still be able to pre-charge the intermediate node, okay, and have the output also maintained as the intermediate node here Y prime can now be pre-charged here with no problem, because the clock, the footer device, turns off the NMOS. So هذه هون سميناها N1 and P1. Here I will have P1 on and N1 off. Okay, and here it is the opposite. Okay, so the other type where doesn't have the footer transistor, so here we remove N1, and this is when the input is arriving from another domino gate. This is when the input is arriving from another domino gate, because the output of a domino gate, let us examine how it looks like. So if I have a domino gate, we know that when the clock is low, that the intermediate node will be high, and therefore the output will be low. Okay, and therefore the inputs to the domino gate from a previous gate, if this is arriving from another domino gate, output, the way this is going to look like, it will always be low, just like this branch here. Okay, when the clock is low, okay, so there is going to be no contention, no problem. And so since the pull down will be off, I don't need to protect. Okay, so in here, these are the inputs. Okay, So yeah, this means that the pull down will be off and no need to protect with footer device. So we only use footer devices when the previous gates are non-domino or when I have primary inputs. Therefore, the addition of the inverter allowed the output to be equal to 0 during pre-charge. This means that it does not activate pull down of next stage gates, but this has implication on the function. In terms of the function, really I have now non-inverting functions. Why? Because during evaluate, if this is my domino gate, okay, when A equals 1 and B equals 1, this node will be pulled down to 0 and therefore the output will be 1. فإذا instead of if Y implements an AND, okay, this node Y here, okay, then out implements an AND because it really requires an inverter afterwards, okay. So this is the idea here. Okay, so now we have the complete picture. I have a circuit with a pull down network. Okay, I have a pre-charge transistor, a transistor that helps me charge. I can have a protective footer device, and those two are connected to a clock. Now, when the clock signal is low, the P is on and the N is off. Okay, and vice versa, when the clock signal is high, okay, the M is off and the P is off and the N is on, and we call this the evaluate phase because it really depends. Now, if my inputs are active, I will evaluate the function and I will pull down the network depending on the logic of my inputs ABC. Now, as the clock cycle repeats, the functionality repeats. So, therefore, for the pre-charge stage, the clock gated pull-up pre-charges the output F to high, okay, and the logic array is typically disabled by virtue of what we have mentioned, that if this is high, the output is low, okay, and if these are arriving from other domino gates, this will also be low, and so the logic array will be disabled, meaning the logic block here will be disabled. Now during evaluate, this is turned off, this is turned on, okay, and now any input signal that is arriving from the primary input will result in the discharge of this node. If it discharges this will become a 1, and as it propagates, the 1 may arrive from other domino gates, and we will discharge my gate, and it will move on to the second stages. Okay, then what happens if I have one arriving from other domino gates during evaluate? This can discharge this node, resulting in a one that will propagate to other stages. So let us take this example. This is the example of, let us see, the pull down network is, so this function here is A, B, C bar, and this is really A, B, C. And so what happens during pre-charge, assuming that A, B, C are always 1, okay, during pre-charge Mn is off, Mp is on, even if these are 1, 1, 1, I don't have a path to ground, I only have a path to VDD. So the node F will be high, okay, node F will be high. And now what happens is that when the clock turns on and the clock becomes high, this turns on, this turns off. Knowing that these are all 1, 1, 1, this is going to discharge the node F. So F will evaluate and drop to 0. Okay, F will drop to 0. And as a result, Y will rise to 1. So F will drop to 0 through this path, and Y will rise to 1. And then when the clock turns low again, when the clock becomes low again, okay, this will be off, and this will be on. And so despite the fact that these are all ones, this is going to pre-charge this, and this will go back to 0 again. So this gets pre-charged, and then this node will automatically drop down to 0. So this is how a typical domino gate with all 1 inputs behaves. Now, assuming that, another example, that the inputs are always 0. So let me assume that I always have primary inputs that are always 0. Then during a pre-charge, this will be on, off, this will be pulled up, so the out will be high, or node F will be high, and Y will be 0. And then during the second phase, the clock will be high, so the PMOS will turn off, the NMOS will turn on. However, these are 0, so I don't have any path. So in this scenario, F will maintain its value, and there is no place for it to discharge, and therefore Y will not rise. Okay, and here what we see, either Y rises or Y does not rise, depending on the values of A, B, and C. Now here in this example, we're assuming that A, B, C are the output of another domino gate. So they only rise during the high clock, and then they fall. So initially they are zeros. Okay, the clock is low, so this is on, this is off, so this is going to charge the output, so the output node F will be high. And then what happens is that during evaluate, when the clock rises high, this will turn off, this will turn on, and the A, B, and C coming from another gate will rise high. Because they rise high, this will be on, and it's going to discharge now the output. So you'll see that the output is dropping to 0, and accordingly, post-inversion, the Y will rise. Okay, now what's going to happen is that we'll go to pre-charge phase again. So this will be on. Okay, the inputs coming from another domino gate are going to drop. Okay, so this will turn off, and also clock is low, so this will turn off. So therefore, we're gonna pre-charge the output again. Okay, and by inversion this is going to drop back to 0. So you will see that the final output here is going to really be a pulse that evaluates to 1 during evaluate in this example or in this scenario. Now let us just take another example. So in the same example, if B does not rise, then there will never be a path for the evaluate cycle to evaluate. So let us take this little scenario here. Pardon me. Let us take this scenario here where okay, so let us assume that a B is always 0. Okay, so under this scenario, during low clock, we agreed that all the inputs were, during low clock, all the inputs were 0. And so this is clock is low, this is on, this is off, it's going to charge. So my output F will start high. Okay, but then during evaluate, A rises, C rises, but B does not. Okay, so although the clock turns on, okay, this is on, but this is off. So there is no way for this to go down. And therefore, in this scenario or example, this will remain high. And therefore, Y will not rise. Okay, so for this scenario, if B is stuck at 0, during evaluate, F out will not drop, and therefore Y will not rise, and I will yield an output that remains 0. Okay, so if we compare the two examples, when the block evaluates, it will result in an output that rises. If it does not evaluate due to logic, based on the logic inputs, then the output will be 0. Therefore, the output can be 0 or 1 during evaluate. Okay, so during evaluate, my output can or may not change. But before evaluate, the output will be 0. And during evaluate, I can have either a 0 or 1. Okay? طيب هلا we will look at from a design perspective the pull down network كون في عنا Euler path اللي هو A, B, C and phi. Okay, and it is between ground and out. And as far as the output is, we only have a clock coming to a PMOS transistor, and we don't have any other PMOS transistors for the design. Okay. So therefore, we have 3 types of logic that we can implement. The CMOS, where I have a pull down and a pull up network. We need an inverter to perform an AND function in this example. The pseudo-NMOS, where we only maintain the pull-down network, we place a keeper or a weak device, weak pull-up device. We have an inverter, we can implement the AND function. The domino logic, where we have a clock, we can have a footer clock as well, and we maintain the pull-down network. Automatically, the design has an inverter, so it implements the domino AND. Okay, thank you.